name is Chris Harris and I'm from Allery Chemistry, and welcome to this video on OCR, enthalpy and entropy. So in this video we're going to look at this topic, and the topic is specifically designed for OCR. So if you're studying, if your exam board is OCR, then this topic is perfect for that. There is this video, and there is a full range of videos for OCR on my YouTube channel, which is Allery Chemistry. All I ask, it's all free. Completely free and always will be. All I ask is that you hit the subscribe button, and that is more than enough for me, just to show you support for the channel. It is specifically designed, like I say, for OCR. There's a full range of resources on there for all the major UK exam boards, so everything is on there. If you want your own personal copy of these slides, they're available to purchase. If you just click on the link below in the description box, they're great value for money and perfect for revision on the go. So if you're on your smartphone, your tablet, then all the information will be at your disposal there. And the whole point of this is to supplement your revision. And it doesn't include, for example, things like doing the exam practice exam questions. So these are purely just designed to kind of refresh your mind. You might have already looked at the content, or this may be from new, in which case it's an introductory thing for you. But it's very important to practice exam questions. It's one thing knowing the content; it's another thing actually practicing it. If any of you are learning to drive, for example, you can read the highway code from back to front. It doesn't mean you hop in the car and start driving, because you may have an accident. So the skills are two different things, and this is exactly the same. But I do have on my YouTube channel on Allery Chemistry, I do have work through videos where we go through past papers, so have a look at them if you're a bit stuck. But like I say, these all are tailored to OCR in particular, and they meet the specification points. This is an extract from the specification, and it just ensures that you know enough to revise from, but no more. Okay, so let's start with the first one, which is entropy. Entropy is a very strange thing. It's got some very weird terminologies in this, but entropy is a measure of disorder in a system. Okay, sounds like some kind of city brawl or something. So yeah, it's a measure of disorder. Nothing criminal here, of course. So entropy is given the letter S. Yeah, what would you expect? It's given the letter S, and is basically the number of ways that energy can be shared out between particles. So it's actually quite a useful energy. For chemists, well, obviously it would be. It wouldn't be in the specification if it wasn't useful. But basically, the more disorder there is, the higher the level of entropy. And so we can look at this in a very simple thing. Yes, I bet you didn't think you were seeing solid, liquid, and gas particle diagrams at A level. You thought they were confined to back to year 7 or something. So anyway, it's a really good model to help explain entropy, so I'm going to use it. So solids have the lowest level of disorder. The particles are arranged neatly in rows, a perfect arrangement. Liquids and then gases are clearly more disordered. So you can see in this diagram here, we start with solids, neatly arranged, moving into gas, and the disorder is increasing, and so is the entropy. So there is an increasing entropy as we go towards substances which tend towards gas arrangements. So the number of particles also affects entropy change. So if a reaction is in the same state, but more moles are produced, then entropy increases. So in other words, if we're going from, say, 4 moles on the reactant side to 10 moles on the product side, then that's an increase in entropy, because we've got more ways in which the particles can be distributed if you've got more particles or more molecules. So an example would be nitrogen tetroxide producing nitrogen dioxide. So this shows an increasing entropy, because we've gone from 1 mole on the left to 2 moles of gas on the right hand side. So we've got more ways in which this can be arranged. Okay, so a reaction can be spontaneous, or that means feasible. So it can just go of its own accord, even if it's enthalpically unfavourable, i.e. endothermic. So you would have known, particularly from year 1, about endothermic and exothermic reactions from your enthalpy diagrams. And if you're not sure, then go and have a look at the year 1 playlist, because I've done videos on that as well. But there is a way in which you can get reactions to go even if they're endothermic, which is strange, because entropically it's favourable. So a reaction will tend more towards disorder and hence an increase in entropy. Okay, I liken this to a little bit like a bedroom, right? It is far easier to have a bedroom that's messy than it is to have it all neatly structured and ordered. And if you want to put it into some kind of order, you have to put effort into that. You have to put energy into that. And so it's easier just to let things just get messy. It's a lot easier. You don't need to do, don't need to put nowhere near as much energy or thought into doing that as you do to putting it in order. Apply the same principle as it is for entropy. So entropy reactions will tend towards a more messy, disordered system. It's far less energy is required, and particles are lazy. Okay, they don't like to be in a high energy state, so they don't want to. So that's the key thing. Just remember that. That's the natural course, is towards increase in entropy. So increase in entropy is energetically favourable, so that's a good thing. Okay, some reactions that are enthalpically unfavourable, like I say, the ones which are endothermic, can still spontaneously react if changes in entropy overcome the changes in enthalpy. So it's about a tug of war. Which one's bigger? Is it enthalpy or entropy? Okay. So, for example, a spontaneous endothermic reaction. Here's an example here. So the reaction between hydrated barium hydroxide and ammonium chloride shows how entropy changes overcome enthalpy changes. So we've got two solids and they're mixed, and a gas, a liquid, and a solid is produced. Okay, so we've got barium hydroxide, hydrated barium hydroxide. So that's what the .8H2O means. That just means there's water attached to, there's 8 water molecules attached to every barium hydroxide molecule. That's all that means. So don't worry about that. But it's a solid. That's the most important thing. Ammonium chloride's a solid as well. So we're going from two solids to a gas, a liquid, and a solid. Now, this reaction can show temperature drops of 20 degrees Celsius. Now, you might have seen this. You might have seen this reaction. Normally it's done where you have a beaker, and all these chemicals are readily available in colleges and schools as well, but it's done in a beaker, and you mix the two solids together, and you put it on a block of wood with some water between the wood and the beaker, and you stick that on, and what happens is that the temperature of the beaker drops so quickly, and it is literally, you can see it very quickly, that the water beneath, between the beaker and the wood freezes, and effectively you can lift the beaker up and the wood sticks to it, and it has a very strong smell of ammonia, which is not the nicest bit, but you get this white paste that's being made as well. So it's a really good reaction to show. Now, normally endothermic, I mean, that just never, endothermic reactions shouldn't happen. You're forming products which are higher in energy. That just doesn't happen. But the entropy here, we're going from solids to gases and liquids, far outweighs that. And so that's why this reaction is feasible. So, summary points. The reaction, this reaction is very endothermic. Enthalpically, it's not favourable. So the value we associate with this one is plus 164 kilojoules per mole. It's not a favourable reaction. There's 3 moles on the left-hand side and 13 moles on the right-hand side. So entropically, it's favourable. Okay, you'll see this a lot, enthalpy and entropy. And the third point is we're starting with 2 solids, but we're making a gas and a liquid. So this as well, on top of the increased number of moles, is increased disorder, so it is entropically favourable. So there's more things going in its favour than there is against. Okay, and you'll see a formula soon. Just looking at an actual formula, yes, another formula. Looking at how you can calculate that, that tug of war, that difference between enthalpy and entropy. Okay, so entropy change can be calculated. Entropy is given obviously the symbol delta S, and that can be calculated between reactants and products. So entropy change, or delta S, is the entropy of the products minus the entropy of the reactants. And we use the energy, the units of energy, is joules per Kelvin per mole. Okay, you've got to remember that. Don't get it confused with kilojoules. Okay, this is the standard units, is joules per Kelvin per mole. Okay, entropy values are given as standard amounts, just like with enthalpy. There's no difference here. It just means we can compare them. So it's always 1 mole of substance, 100 kilopascals, 298 Kelvin. You must remember them standard conditions. Okay, so let's look at an example calculation. So let's bring back that reaction that we'd seen before, that really cool reaction. So the reaction between hydrated barium hydroxide and ammonium chloride, and what we need to do is calculate the change in entropy. So you'll be given the data, you're not expected to know the data. So there's the data there, just popped up in the bottom right hand side. So we've got all the entropy values for all the different substances that we've got in that reaction. So it's products minus reactants. So the products, let's look at the product side. So we have 2 lots of ammonia, okay? Remember, we've got 2 here. You've got to take into account the value at the top as well. So we've got 2 lots of ammonia, 10 lots of water, and we've got 1 barium chloride substar compound molecule here, which is on the side. So if we add all that up, we get a total entropy change of 1208 joules per Kelvin per mole. Okay, so that's the product side. We then do exactly the same for our reactants. We've got 1 molecule of barium hydroxide that's hydrated, and we've got 2 of ammonium chloride here, which is this substance here. So we add all that up and we get 617, and it's very simple. All we do is we do 1208 minus 617, and we get a total entropy change of 591 joules per Kelvin per mole. Okay, so entropy is positive, so it's a positive value, so that means it's entropically feasible. So a positive value for entropy is good, because that means we get a reaction that's feasible. A positive enthalpy value means that it's endothermic and is not feasible, so don't get them confused. Okay, positive entropy means favorable. Okay, so remember when I was talking about making the link between enthalpy and entropy and this tug of war and how you calculate it? Well, thankfully, there is a formula, and we call it Gibbs free energy. And Gibbs free is actually sensible. It's given delta G. Gibbs free energy tells us if a reaction is feasible or not, which is brilliant, because it means we know if it's going to work. Before we even do the reaction, we can work out if this reaction is actually going to go. So this is prediction at its finest. If only the Gibbs free energy told us the lottery numbers, that would be even better. But anyway, delta G equals delta H minus T delta S. So that's the formula. Delta H is enthalpy, okay? So we're going to use enthalpy in joules per mole, okay? It keeps it all the same. So if you're given enthalpy in kilojoules per mole, you're going to have to multiply it by 1,000 to get it to joules per mole. T is temperature, always in Kelvin. And delta S is entropy change, which is in joules per Kelvin per mole. So if we have all our units in the same standard, that means we don't have to worry about what delta G is going to be. So units of change in free energy is joules per mole. Okay. So the basic rule, okay, very easy. If a reaction is feasible, in theory, okay, delta G is negative or 0. So if it's just feasible, it's 0. If it's negative, it's feasible. Okay, so theoretically, that's what we're saying. So you've got to remember that, because that's what we're going to use in a minute. What we've got to be careful of, though, is that even if a reaction is calculated to be feasible, okay, you might not observe a reaction actually occurring in front of your eyes. And this may be because the activation energy is actually too high, or the rate of reaction is very slow. So you've got to remember, when we looked at enthalpy diagrams back in year one chemistry, you know that you've got to have enough energy for a reaction to happen at all. You've got to have enough to breach the activation energy. And just because Gibbs free says it's feasible, it may not be. You may need to add a catalyst, or it might be incredibly slow, in the fact that it's so slow that it takes years to work. For example, a classic example is rust. You can put a bit of iron out there and leave it. It would take a while to rust. You don't see it literally reacting in front of your eyes, but it's a feasible reaction because we can see things rusting. It just takes a while for it to happen. Okay, so calculate the free energy, or delta G, for the reaction between barium hydroxide and ammonium chloride at 298 Kelvin. So it's that same reaction again. So we know the following from the previous slide, that delta S is plus 591 joules per Kelvin per mole, because we worked that out from the previous equation. And the enthalpy change is 164 kilojoules per mole. But remember, what we should do is convert that into joules per mole by multiplying it by 1,000, because that keeps everything into the same format, same units. So delta G is delta H minus T delta S. So delta H is 164,000, because that's our enthalpy change for this reaction. Okay, and it's positive. Remember, it's a positive value because it's endothermic. Minus temperature is 298. We're doing this at room temperature, and delta S is 591 because we've just worked that out. So the value, delta G, is minus 12,118 joules per mole. That negative value, remember, tells us that this reaction is feasible at room temperature, and indeed it is when we do it. Even though it's endothermic, the entropy value is so large that it completely outweighs the delta G. So delta G is negative, so it's feasible. Now see it, because you'll see this later when we look at theoretical tests towards this, but split this equation up into two bits. It makes it a lot easier. So you've got a delta H bit, and you've got your delta S bit, and your T is lumped in with that, okay? So if this bit here is bigger than that bit, then delta G is always going to be 0. If this bit here, your delta H, is bigger than that bit, then your delta G is always going to be positive. So it's this balance between delta H and delta S, okay? But try and see it as like two halves of the equation, and that makes it a bit easier when you're predicting if a reaction is going to go. Okay, so how do we calculate delta H? So energy from colorimetry experiment can be calculated, which can then be used to calculate delta H. Okay, so we use this formula, which is Q equals MC delta T. Okay, and we use this setup here so that you might have seen you might have done this in year 1 chemistry, and you might have done it actually in this year as well. But you do need to know the calculations for this. So for OCR, it's probably more likely you might not have done it in year 1 yet. But Q equals MC delta T, and Q is the heat energy lost or gained. Okay, they keep giving you letters which don't actually match anything that you might have seen, but anyway, Q is energy lost. Mass is M is the mass of water or the solution in grams, depending on what they're giving you. C is the specific heat capacity of water, which is constant. That's 4.18 joules per grams per Kelvin. You'll probably be given that in the exam, but you'll probably use it that often. You'll just remember it anyway. And T is the temperature change, and that's always given in Kelvin. So let's look at an example. So let's say if we have 100 grams of water was heated from 23 degrees Celsius to 57 degrees Celsius by 1.8 grams of ethanol. So that's the amount of fuel we've used to do that. Calculate the energy transferred and hence the enthalpy change of the fuel. So Q equals 100 grams because we've got 100 grams of water, that's the mass of our water, times by 4.18 because that's the specific heat capacity, times by 34 because that is the temperature change. So we've done 57 minus 23, and that gives us a Q value of 14,212 joules or 14.2 kilojoules. So we've got to calculate the energy first. Okay, that's the first thing. So when working out delta H, remember the units of delta H is kilojoules per mole. We've got to work out the kilojoules bit first, then we'll work out the mole bit afterwards. So this is where we're going to work out the moles. So the moles is the moles of ethanol. So moles is mass over MR. And we know that we've used 1.8 grams of ethanol because that's the mass. And the MR of ethanol is 46. And obviously you'd use your periodic table to work that out. And the moles is 0.039. So this is the number of moles. And then because enthalpy is kilojoules per mole, we do kilojoules, which is energy, divided by moles, because it's kilojoules per mole. So, okay, so you've just worked out the two different parts. So here it is here. So enthalpy is Q, which is energy, divided by moles. So it's minus 14.212, which is the energy side of it. That's the enthalpy that we've used. And then it's divided by 0.039. The reason why it's negative is because we're giving heat out. It's an exothermic reaction, so we have to put a minus in there. So the enthalpy value is minus 364.4 kilojoules per mole. So it's important to put that minus value in there as well. Okay, so enthalpies of solution can be calculated too. So what we looked at there was the enthalpy of a mass of substance. So here we're going to look at solutions. So this might be where you mix a compound together. So you might mix two solutions together and they may form an exothermic reaction or an endothermic reaction as two powders, as we've seen before. So this is where we're mixing solutions together instead of using a fuel to heat it up. So what we have is a solution in a polystyrene cup, and we put a lid on that to prevent heat loss. So we try and contain all that to try and reduce errors. So we add an acid first, so we measure the temperature. So we chuck our acid in. This case, we're going to use an acid-alkali reaction, acid-base reaction. So we add our acid in there, measure the temperature. We then add an alkali or solid, and then we stir and measure the temperature change. Okay, and we measure that at regular intervals. It might be every 30 seconds, every minute, whenever you would like to do that, whatever is appropriate. So let's look at this example. So we've got 25 centimeters cubed of 1 molar HCl, hydrochloric acid, had a temperature of 20 degrees. 25 centimeters cubed of 1 mole dm cubed sodium hydroxide was added, and this raised the temperature to a maximum of 26 degrees Celsius. Okay, so it's raised it by 6 degrees maximum. We need to calculate the enthalpy of neutralization for hydrochloric acid. Okay, so it's a little bit trickier, this one, but follow the same rules. So work out energy first. So Q is 50 times by 4.18 times by 6. So the 50 comes from the combination of 25 centimeters cubed of acid and 25 centimeters cubed of sodium hydroxide. And we assume that the volume in centimeters cubed is the same as grams, so the density is just the same. So that's why we use 50 there. 4.18 is heat capacity, and 6 is the temperature change because it's risen by 6. And then we get our energy, which is 1254 joules or 1.254 kilojoules. So the moles of hydrochloric acid, we're looking at the moles of hydrochloric acid because that's what we're looking for, is the enthalpy of neutralization for hydrochloric acid. So the moles is concentration, which is 1, times by the volume. Now, notice the volume is 25 centimeters cubed. So what we're going to do is we need to convert that. Into decimeters cubed. So we do that by adding times 10 to the minus 3. Now, I like doing it this way. You can do just divide by 1,000, but I like to add just times 10 to the minus 3 in the end, and it means you can just punch it all into the calculator in one go. But it's up to you. That's just my method. That's what I would prefer to do. But you can easily just divide it by 1,000 and gets you the same result. The moles is 0.0250. So we worked out the moles of acid. So then we have to work out our enthalpy, just like we did before. So it's energy divided by moles. So the enthalpy, because it's an exothermic reaction, we put minus 1.254 because it's giving out heat energy. Divide that by 0.0250, and so our enthalpy change for this reaction is minus 50.16 kilojoules per mole. Okay, so fairly straightforward. Okay, so let's go back, because we've looked at entropy, we've looked at enthalpy, and we've looked at how we can combine them to form Gibbs free. So what we're going to do is take all that information that we've got there and do something useful with it, using entropy and enthalpy. So temperature may have an effect on a reaction feasibility. Okay, so let's look at different scenarios when we've got our enthalpy and entropy is changed and what the value of delta G is. So this is what I was saying about taking the delta G equation and splitting it into two halves. And this is, by doing it that way, this makes this bit a lot easier. Okay, and you'll see what I mean. Okay, so let's have a look. So delta G, remember, for something to be feasible, it must be, in theory, it must be negative or 0. Okay, that's the key concept here. So what we've got is different information here for delta H and delta S, and we've hypothesized. So we've looked at, if delta G was this and delta S was this, what would the value of delta G be, and is it feasible? So what we're looking at here is this table. So like I say, it's easier to split it into two halves. So we've got delta H and the T delta S part. It's much easier to look at that. So let's have a look. So look at the first row. So even if T was at its lowest, so let's have a look here. So this is the T bit. Even if T was at its lowest, which is 0 Kelvin, delta G would always be positive. Would always be negative. So exothermic reactions with positive entropy would always be feasible, whatever the temperature. So you can see here, anything, soon as you see that it's negative, so it's an exothermic reaction and entropically favorable, it will always be feasible at any temperature. Even if that was 0, the temperature, it would always be feasible. Okay, so that's the first bit. So if we look at the second one, the second row, even if T was at its lowest temperature, which is 0 Kelvin, delta G would always be positive. So endothermic reactions with a negative entropy would never be feasible at whatever temperature. Okay, so try it. You put any number into that equation, and you will always see it would never be feasible. So let's look at the third row, which is this one. So freezing water is an exothermic process, okay, because it's giving out heat energy when it's freezing. So delta H is negative, but we are going to get more ordered arrangement. Okay, so basically we're going from a liquid to a solid. We're going to a phase where entropically it's not favourable, but enthalpically it is because it's exothermic. Okay, so freezing only happens below a certain temperature. So water won't freeze unless it's at 0 degrees Celsius. So it depends on that scenario. So if delta H is negative, delta S is negative, it might work, but it will only do that if the temperature is low enough for it to do that. So a good example, like I say, is ice. And let's put some numbers into it just to show you as an example. So if we've got delta H, that's the enthalpy side, is minus 100,000 joules per mole, and the delta S is minus 100 joules per mole, then at 500 Kelvin, so if we put that in here, so minus 100,000 minus 500 times by minus 100, so this is putting it into this formula here, delta G is minus 50,000, so therefore it's feasible because that's a negative value. But let's say if we increase the temperature, and we did it at a higher temperature, then we put the same numbers in, but notice we get a delta G at plus 50, so it's not feasible. So you'll see the effect of temperature, all we've changed there is temperature. So it is feasible at a lower temperature, but not at a higher temperature. So this is where we can try and hypothesize about what happens. Okay, and let's look at the last one. So this is the fourth row. So look at the fourth row. The decomposition of sodium hydrogen carbonate is an endothermic process. So that's not a favourable process. So delta H is positive. But we're going to have a more random arrangement because we're going from a solid to a gas. So it's favourable entropically. So that's a good thing. But this happens only above a certain temperature. So unlike the freezing of ice, where that would only happen below a certain temperature, this is happening above. So a classic example, like I say, is the decomposition of hydrogen carbonate, and that's used to make cinder toffee. Okay, so you can see we're going from a solid to a gas, and obviously as this bakes in the oven, you get gaps, you get holes because of gas pockets that have developed. So this is like a crunchy bar. So let's have an example. So put some numbers to it. Again, enthalpy is 100,000 joules per mole. Entropy is 100 joules per mole, exactly the same. So let's look at it at 500 Kelvin. We get a delta G of 50 plus 50, so that's not feasible. But if we increase the temperature, we get something that is feasible. So that is 50,000 joules per mole. So that's a feasible reaction. So above a certain temperature, these reactions do go. But it really does help to split that equation in half and look at it in two halves, and it makes it a lot easier. So that's fine. Now what we can do is we can now, and this is really useful for industry, because we can now actually work out, well, what temperature is it feasible at? Because why would you heat something that more than it needs to be? It's just a waste of energy. So if a chemist can work out what is the minimum temperature we can get away with just to get this reaction to go, then that would be useful. And this is again where Gibbs 3 comes in. So it's so versatile, as you can see. So a reaction is just feasible, remember it, when delta G is 0. And what we can do is we can rearrange that equation to work out the temperature when delta G is 0. So T equals delta H over delta S. Okay, so that's when we remove the temperature bit, and we put temperature as the subject. So we notice that, we've removed delta G. So we remove delta G because delta G always equals 0. So because it has no value, we don't need to include it in our formula. So this is the rearranged equation that we have. T equals delta H over delta S. So what we need to do is calculate the minimum temperature required for sodium hydrogen carbonate to decompose. So here's sodium hydrogen carbonate, and then we form sodium carbonate, water, and carbon dioxide. Enthalpically, this is positive, so that's an endothermic reaction. It's not feasible normally, but it is above a certain temperature. So here's our entropy values here, so for each of the different substances. So the first thing we need to do is work out what delta S is. Okay, we've done this before in the previous slides. So delta S is products minus reactants. So we add up all our products, which gives us 539 joules per Kelvin per mole, so we use the table. Add up all our reactants, which gives us 204 joules per Kelvin per mole. And then we do products minus reactants, and that gives us a total entropy change of 335 joules per Kelvin per mole. So we've got the delta S bit, so that's good. We've got our enthalpy bit because they've already given us that. So now we can use this equation. We've got to assume that delta G equals 0 because that's the point at which it's just about feasible. So we do delta H, which is 129,000. The reason why it's 129,000 is because we need to convert, remember, kilojoules into joules. So we multiply by 1,000. Divide it by 335. And that gives us a minimum temperature at which this will go is 385 Kelvin. Anything above that will definitely be feasible. Anything below that, and it won't work. So this is really useful because it means that as a chemist, we can now say, right, well, we need at least 385 Kelvin. So we know that we've got to make sure that the minimum temperature for this reaction to go must be 385. We could do it at 400 if you want, or 450, but that could be a complete waste of energy. Why heat something up more than it has to be? Okay, and that's it. So that's everything on enthalpy and entropy. So a bit of one of the shorter topics. Like I say, all the videos, there's a full range of videos for OCR for year 1 and year 2. Just have a look on the YouTube channel. You'll find them all there. Please subscribe to the channel. That's all I ask. They're all for free. You don't have to pay for them at all. If you want a personal copy of these slides, then if you click on the link below and you can access them, you can purchase them from the test shop. So they're all there, and just go and have a look, and great for revision, etc. But that's it. Okay, bye bye.